Hello everyone, it's Dr. Paul Rose here, and in this presentation I'm going to be looking at the Spread of Participation Index that allows us to measure how animals in the zoo use the space they are provided with. This is a worked example that uses data from one particular formula of the SPI that is really relevant to when you're dealing with complex exhibits with ranges of different zones within them. And here's what I mean by a complex exhibit that contains a range of zones. This is the enclosure that I'm going to be using for this case study. It's a large walk-in aviary and it contains a number of different bird species with very specific ecological requirements. You can see that the enclosure complexity provides the animals with a range of resources that they can directly interact with. And these resources and areas of biological relevance are really important when it comes to measuring space use by using the SPI formula, because you're basing where the animals are on their preference for occupying particular zones within the enclosure. This enclosure is home to 4 species of specialised wildfowl. At the top left we have the common scoter. At the top right, we have the long-tailed duck. At the bottom left, we have the Chinese or scaly-sided merganser. And at the bottom right, we have the harlequin duck. So this exhibit is having to cope with the ecological requirements of these 4 species. Some of these ecological requirements are similar, but others are very species specific. And you can see the different shapes of the duck's bills give us an indication of their different foraging needs, and therefore that would be an example of biological need that would be built into the features within the enclosure. When we use the SPI to measure space use in the zoo, we have different ways of doing this. We could use the traditional SPI, formulated by Dickens in 1955, which splits up an enclosure into equal zones. And here in my example, you can see how an enclosure that contains a pool, a nesting area, a feeding area, some shrubs and bushes, a public accessible area, and the animal's house has been divided into 8 rectangles of the same size. This works well when enclosure complexity is low, but in this case, favoured zones that might influence why the animals will be there because they contain something of real importance in the exhibit are now split between different areas, and this may bias estimations of space use because we're not entirely certain which part of that zone is being used based on the split in the resource. The modified SPI is the example calculation that I will be using in this example. Instead of splitting the entire exhibit into areas of equal size, the modified SPI calculates area based on the specific zones that the animal has access to. In this case, the house would be a zone, the pool would be a zone, the feeding area would be a separate zone even though it's contained within the pool. The nesting area will drive behaviour in a particular direction at particular times of the year. Therefore, that would be a standalone zone. The grass that surrounds everything is also its own zone. The public area, if accessible to the animals, would also be a zone that they can engage with, as would all of the bushes and shrubs. So the modified SPI allows us to calculate enclosure usage based on the animal's occupancy of biologically relevant resources that are provided within the enclosure, and we call these biological relevant resources the zones that the animal has access to. So let's have a look at some examples of zones within this aviary. We could say that the waterfall is a zone. It's a standalone section of the pool, it has a stream leading into it, and therefore the animals can do different things in the waterfall than they can in the pool itself. We have the land area around the waterfall, which is steeper than the bankside vegetation that you can see on the right-hand side. Again, the birds can do different things in this part of the terrestrial environment than in others. And then we have the pool itself, which we could keep all together as one zone, or we could split if there were areas of different depth or accessibility of the water, for example. So here in this one photograph, we've created different zones based on the available and usable space that the animals can interact with. And if we look at all perspectives of the enclosure, as you can see in these two photos from either end, we can actually identify 6 defined zones of ecological relevance within this aviary. We've already mentioned the pool, and we've already mentioned the waterfall. We can look at the land that is furthest away from visitors. We can look at the land that is closer to the visitors. We can look at the rocks and boulders that are provided within the pool for perching or resting. And we can also consider the shrubs and denser planting around the edges of the enclosure as a biologically relevant zone too. All of these things will be used by the birds at different times of the year and for different reasons. Therefore, our best estimation of spatial use in this enclosure is to break it down into ecologically relevant zones and to apply the modified SPI formula to where we see the birds from our observational data collection. And this is the formula that we would use to estimate space use within that enclosure by using the modified SPI, published by Plowman in 2003 in Applied Animal Behaviour Science. If we break this down by the top and bottom of the formula, the top of the formula has FO, which is the observed frequency, what you have seen within which particular zone, and from that we subtract FE, which is the expected frequency. If enclosure usage across all zones was random, what would we expect to see the animals doing, i.e. occupation rate of that particular zone? You will note that FO minus FE is within vertical or modulus brackets. That means the resulting amount from that subtraction is always positive. We then have the sum sign at the front of that top part of the formula, so we add together our FO minus FE for each of the zones that we have calculated. I said that this enclosure contains 6 zones, so we would sum together the FO minus FE for zones 1, and then for zone 2, and then for zone 3, and then for zone 4, and so on. The bottom line of the formula contains large N, which is our total number of observations that we have seen across all zones, and we subtract our expected frequency from the minimum zone, which is the smallest zone. So FE min is our expected frequency of observations in the smallest zone. We do all of that in the brackets first, and then we multiply that by 2. To ensure that we have no bias within our equation, our FE min should ideally be greater than 5, because this helps to prevent any bias in how we are breaking up the exhibit into particular sized zones and how the animals might be using their space. If the zone is too small that the animal can't fit into it, we've created bias in our own calculation. Whilst the SPI formula might look complicated, it's actually relatively easy to follow. Using zones of unequal size helps prevent underestimation of enclosure utilisation. As I've said, we are not equally defining the exhibit into areas of equal size. That takes into regard none of the biological relevant resources available. By using different zones, we're able to work out how much of the enclosure is made up of that particular zone, and therefore how long the animals are choosing to spend in it. For our formula, the observed frequency is simply the number of times the animal was seen in that area. For an individual, that could be the amount of time it's spent in that zone, or for a group, it could be a count of the number of animals out of the total population seen in that zone. And the expected frequency is the first part of the formula that you have to work out. The expected frequency is the same for all zones in the enclosure, regardless of how many different species you are observing. We are comparing all species back to the same expected frequency of occupancy. And the expected frequency is the relationship between the observations seen in that particular enclosure area and the ratio of each zone out of the total area of the enclosure overall. So the formula for calculating the expected frequency is to take your percentage area of the enclosure and divide it by 100, and then to multiply that by your total observation time that you've collected data over. These data here are what we have seen the birds doing in that particular exhibit. So we have our 4 species of long-tailed duck, scaly-sided merganser, harlequin duck and common scoter. And I hope you can see that in each zone we have an observed frequency of occupancy. Simply, how much time has each animal spent within that particular zone? So our FO, our observed frequencies, are simply where did you see the animal? What data did you collect on zone occupancy? In this case, for each individual bird, it's the number of minutes out of a total observation time of 500 minutes that individual of each of those species spent in each of those zones. So the long-tailed duck didn't spend any time in zone 1, spent 269 minutes in zone 2, 175 minutes in zone 3, no time at all in zone 4, 56 minutes in zone 5, and no time at all in zone 6. So those observed frequencies are out of the total observation time. Now we have our observed frequencies from our actual data collection and behavioural observation on the birds. Let's look at calculating the expected frequency to compare what we have observed with what we would expect if enclosure usage was random. The first thing you need to do for any enclosure is measure or estimate how much of each of your zones makes up out of the overall size of the enclosure. So in this case, zone 1 is the waterfall, and we've estimated that as 20% of the overall available area. The pool is zone 2, and we've estimated that as 45% of the area. 5% for zone 3, which are the rocks and boulders in the pool. 15% for the bank nearest the visitors, which is zone 4. 10% for the area which is the bank away from the visitors, which is zone 5. And zone 6, which are all the shrubs and bushes that are growing in the exhibit, we've estimated that at 5%. So 20 plus 45 plus 5 plus 15 plus 10 plus 5 should add up to 100%, which is the overall amount of space the animals have in that enclosure. Let's now look at how we calculate the expected frequency for this enclosure. Remember, to calculate your expected frequency, you need your overall sample time. So in this case, that's 500 minutes from our observed frequencies. You need your estimated percentage area of the enclosure, and you divide that by the total space available. So for zone 1, 20% divided by 100, which is obviously the total, gives us 0.2. 0.2 multiplied by the overall observation time of 500 minutes gives us an expected frequency of occupancy in zone 1 of 100 minutes. Let's do it again for the second zone. Estimated percentage of 45% out of the total of 100% gives us 0.45. Multiplied by the number of minutes in the overall sample time, which is 500, gives us an expected frequency in the second zone of 225 minutes. Here you can see our observed data and our total observation time. And underneath, we have our areas with their estimated percentages of the total. Here is the formula. Each of these is the expected frequency for each zone. So just as I ran through on the previous slide, expected frequency of 100 minutes for zone 1, 225 minutes for zone 2, 25 minutes for zone 3, 75 minutes for zone 4, 50 minutes for zone 5, and 25 minutes for zone 6. So we have taken the total recorded OBS, 500, and we have taken the percentage area, in the case of zone 120, divided by the total and multiplied it by 500. Your expected frequency is the same for all times that you calculate the SPI formula, regardless of how many species you have in the enclosure. The zone sizes do not change, even though you might be calculating multiple species SPIs. The only time the expected frequency will change is if you don't have the same total time for your observations across all species. So we now have our expected frequencies, and we have all of our observed frequency data. Let's now calculate an SPI for the birds in this exhibit. We've got our different zones, we've watched the birds and collected our data, and we've calculated where we would expect to see them if this was occurring by chance. Here in this Excel spreadsheet, at the top, I have my species of duck, and I have my observed frequency in each zone. Here are my total observations. Here you can see I have copied over the expected frequencies from that calculation. Remembering what I said to you, that the expected frequency will be the same for all birds because they're all in the same enclosure with the same resources, and they have all been observed for exactly the same amount of observation time. These are observed, these are expected. Let's now start by filling in the SPI formula. What you can see here is how I've calculated the observed minus the expected for the zones that the long-tailed duck was seen within. So if I click on this cell in Excel, B2 is what I saw, which was 0, minus J2, which it should have been for 100 minutes. This one here, C2, it was in that zone for 269 minutes. It should have been 225 minutes if it was random, so I get 44. And I've done that for each zone. So this calculation here is my observed minus my expected. And we do that for all birds. And here is my observed minus expected for each zone for each species. Remember, I said to you that that top part of the equation for the SPI formula contains modulus brackets. So on the top line of the SPI formula, FO minus FE is in vertical brackets. Before we sum together each FO minus FE for each zone, we must make sure we turn the resulting mathematical output to positive because of those modular brackets. And this is what I've done here. These are my expected minus observed data. So I have simply copied this table here, but I've now made sure that all numbers are positive. And we can now begin to put together the top line of the formula. And this would simply be the sum of our observed minus expected across all zones. So let's do that for the long-tailed duck and see what we get. These are my positive outputs from each observed minus expected. And that's given me 400 for that top part of the formula for the long-tailed duck. We can copy that down based on how I've laid out the data in Excel. And there is my top line of the formula for each of those birds. So just to repeat myself, FO minus FE for each zone. Ensure you turn the resulting mathematical output as positive and then add them together across each zone, and make sure you do that for each individual animal. Let's now calculate the bottom part of the formula. The bottom part of the formula is 2 multiplied by the overall observation time minus the expected frequency in the smallest zone. So we always do what is in the brackets first. So we know that our N is 500 minutes. Our total obs was 500 minutes for each bird. And we know that our expected frequency in the smallest zone is 25 minutes. We can see that in zones 3 and zone 6. So our FE min is 25. 500 minus 25 is 475. Now remember, we've got to double that. We've got to multiply it by 2. So 2 times 475 gives us 950. So our bottom section of the formula is 950. And again, because we have looked at each animal in the same enclosure for the same amount of time, and all of our total obs and all of our expected frequencies are the same for each bird, the bottom part of the formula is 950 for each animal. So what we have done is summed together our FO minus FE, remembering that each of those is now positive because of the modular brackets, and 500 minus 25 multiplied by 2 is our bottom section of the formula. So we can now calculate the SPI by taking the top and then the bottom and doing the division. And what do we have here? An SPI of 0.42 for the long-tailed duck, an SPI of 0.52 for the merganser, an SPI of 0.55 for the harlequin duck, and an SPI of 0.47 for the common scoter. This is really useful because it allows us to compare individuals in the same environment to see why there might be bias according to how they are using the space provided. Let's now look at how we would interpret these SPI results. If you get a result from your SPI calculation that equates towards 0, this suggests equal occupancy across all zones of the exhibit. Whereas if you have a result that tends towards 1, this suggests more favoured occupancy of some zones compared to others. This is suggestive of bias in the animal's usage of space in the enclosure. This unequal enclosure usage may require further investigation for you to understand why aren't these animals using all of the space they are provided with. It is important to remember that just because we see differences in space use between individuals and the fact that not all zones might be occupied doesn't necessarily mean an animal's welfare is poor. Season and time of day changes will influence when animals use their space. And likewise, an individual's physiological state and its development will also affect how and when it occupies certain areas of its exhibit. We would have to calculate SPIs across multiple occasions and consider behavioural data and health-related information, such as body condition scores, before we were able to accurately state that biased enclosure use and SPI values towards one were suggestive of poorer welfare. If you'd like to know more about how we interpret space use in the zoo as a welfare measure, and how we do different types of recording of behavioural data in the zoo, do please check out my various YouTube videos and journal articles that I've written on this topic. I have a YouTube video entitled "How do zoo animals use their enclosure?" which provides a more broader overview of why we would want to study space use in zoo and aquarium animals. I have a paper published in the Open Access Journal of Zoological and Botanical Gardens, with my co-author, Dr. Lisa Riley, that provides explanation of 10 useful methods, one of which being space uses methods, that might be relevant to those of you wishing to do more zoo animal science. And for those of you wishing to have a very specific example of how enclosure usage data can inform on animals' responses to their environment in the zoo, do please see the paper that I published in conjunction with my research student Ryan that correlated time activity patterns and enclosure usage data of Sitatunga, an African antelope, to better understand how the animals were using their space and why they were using their space in that particular manner. Thank you very much.